Good afternoon, everyone. I hope you had a wonderful morning session with Automate.5. We'll wait for a few minutes so that other people could join. And you can also ask your friends to join the meeting as it will be covering in-depth machine learning practices. Our speaker will join in a few moments, everyone. So before our speaker joins the session, I would like to introduce you to Horizon. Our ISTE is Tech First, annual Tech First. Horizon is an event conducted between 9th to 11th April. We'll conduct various workshops, webinars in Horizon. This is about us, ISTE-VIT. We're conducting a workshop on web dev where we will be building a mobile music app called Mellow. It is a great app. And we are actually building it using React.js in the front end, Node.js in the back end. And then the session you are interested in, Automate.py, we'll be building a voice assistant with Python. We conducted a session called Photonics, and we discussed about various UI UX designs and also about Adobe XD, which was conducted on April 6th. And before everything else, at March 20th, we conducted Code Asymptote, which is a wonderful session. We taught our participants about various data structures and algorithms. And finally, we have a 48-hour hackathon called Technica. In Technica, where participants will be hacking their way and they'll be participating and winning. The details of these events will be given in the comment section or chat box. In a few minutes, our speaker will join the session. Good afternoon, sir.
Good afternoon, Raj.
Sir, can we start our session, sir?
Yeah, definitely. Hi, everyone. My name is Vinod Kumar Sunkara. I'm a senior software engineer at Facebook in Washington. Uh, and I work on the machine learning systems, especially in the search at Facebook. I worked at Yahoo and Microsoft before and currently at Facebook. And some more intro about me is basically I'll talk about it when we get into the session. Um, do we have everyone here, Raj, or do we need to wait for more people to join?
We can begin our session, sir.
Okay.
I'll begin the session, sir.
Yep. Let me share the screen first. Let me know if you can see my screen.
Yes, sir.
Okay, you are able to see my screen, right?
Yes, sir. I could see your screen, sir.
Okay. So again, hello everyone. Today's agenda would be like I'll talk about my journey a bit, and then Facebook, my role at Facebook, and then we'll just jump deep into the machine learning deep dive, different ML concepts, overview of it, and I hope it will be very helpful for you guys uh, to develop your and to find your passion in machine learning, especially. Um, my journey, right? I did my BTech in computer science at IIT Kharagpur. After that, I joined Yahoo. I worked at Yahoo California, and then moved to Microsoft in Washington. While at Microsoft, I did my master's in machine learning, in computer science with machine learning specialization again. After that, I moved to Facebook into the machine learning teams and started working on it. I work in Facebook search and other recommendation systems, utilizing the ML techniques, right? I also work on the backend stuff. Say you search for Vinod on Facebook, and whatever happens in the backend, how the distributed systems handle scoring. There could be like millions of Vinod profiles, right? Like we train an ML algorithm, ML model, and then that model is used to score these different profiles, and the scoring is done by different machines, and finally we combine the output and show you the top 10 or top 5 profiles you see. So that's the gist of what I do, and I work on other recommendation systems also. Um, and it's so much fun to work on ML. If you haven't done any courses or did any ML projects, I would really encourage you to get started after this session. And then let's jump into the machine learning concepts overview. Initially, I'll start with the ML versus AI versus deep learning. But if you have any questions in the middle, uh, please feel free to interrupt. Put your question in the chat box, and Raj, do interrupt me if there is any question. That way, it would be more engaging. So ML versus AI versus deep learning, right? AI is, I know that these terms are very confusing and people would use them as synonyms also. Um, but actually AI is to mimic the human behavior. It's human intelligence exhibited by machines through explicit programming or ML. So artificial intelligence could be through programming or some rules, or through machine learning, right? Then what's machine learning? While artificial intelligence is just to mimic the humans, machine learning is where the machine learns on its own from some data. It can take some data and learn on its own, and develop some intelligence. That's machine learning. And while deep learning is a subset of machine learning, which is inspired by the structure of human brain, that's deep learning. So basically, deep learning is subset of machine learning, subset of artificial intelligence. If you were confused about these terms, now you know. You can see that artificial intelligence is like mimicking humans, and machine learning is actually learning from some data and giving you the output. Uh, could be a decision tree or any algorithm. And deep learning is basically where you have the algorithms mimicking our human brain, and different types of ML techniques. Uh, you must be aware of this if you took any machine learning courses. If you haven't, if this is the first time, like, can I have in chat like how many people are seeing this for the first time? Like, if you are seeing this in the first time, just say hi or something. Raj, do you see any people saying hi?
Yes, so there are some.
Okay, sure. Yeah, I don't see the chats here. I'm just
Yes,
presenting,
sir.
right? So different types of ML techniques. So supervised, unsupervised, reinforcement, and semi-supervised. These are different types. Supervised is like a machine sees some examples with the label, and then it learns from it. And algorithm correlates the features using the label. For example, right? You want a machine to classify a fruit into some categories like apples or bananas. Supervised is generally where the training data will have some features like the shape of it, taste of it, color of it, and then a label. Label is it says whether it has the answer. It says whether it's an apple or banana or what fruit it is. And you have like thousands or millions of training data samples like this. and model tries to learn from it, and when you are given a new data point, it will identify what fruit it is. This is supervised learning. What's unsupervised learning? Unsupervised learning is there's no label. You have all the feature information like shape of the fruit, color of the fruit, but you don't know what fruit it is. So the machine has to learn from the data. It has to identify the patterns and get the clusters, it clusters the like things into a separate section. You don't have the answer for each training data row. Machine has to learn on its own the patterns. That's unsupervised learning. And coming to reinforcement learning, right? It's similar to supervised, but supervised, after for every training sample, you have a training label that tells AI whether we did right or wrong, right? Like if you're classifying an email as spam or not spam, you have some features based on that you would identify it's a spam or not. In the training data, you have that information. But in reinforcement, what happens is you don't know the label, or what happens here is there's a reward to your actions. When you perform some actions, like in a game of chess, you perform some actions and action, and then if it finally leads to a checkmate, then you will give a reward to the model, and it learns from it, and then it gets into the next cycle of learning. Reinforcement learning is basically model learns from the rewards you give to the actions. um, Semi-supervised is like data set comprised of both labeled and unlabeled data. So for some part of the data you have the label, what fruit it is, and for some other part you don't have the label. So this is the illustration of the supervised learning, right? We were talking about it. You have apple, banana, mango, the different fruits, and you have the labels, and you have some features also like the shape, color of it, and the algorithm learns from it, and then it has a trained model output, and this model takes a new input. For here, you can see it took a green apple, and it detects that it's an apple from the learning it had. That's supervised learning, right? And unsupervised learning, you don't have the labels. You don't know what foods these are, but you just have some features. The model interprets and clusters these into three different clusters. You can see apple, banana, mango. Here you just have the model output. Here you have the clusters actually. Now, if you are given a new input, it can try to say it's an apple, similar to the previous section, right? Um, that's unsupervised learning. And a live example is basically if you see some kids at a party, you don't know anything about them, you try to cluster them based on gender and dressing style. That's unsupervised learning. You don't know anything, but you just do some clustering, you do some pattern identification just from the data you have. And reinforcement learning. Let's take a example of a game where a bot has to move from its start to some target. Say this is the target, bot has to move there, and all the actions it can take is up, left, down, and right. Um, initially it explores, and it goes takes different paths, right, left, and finally this is in the second image you can see it has gone through some path and it finally reached a target. Once it reaches the target, it gets a reward +1, and all the grids in the path will get some number. The grids that are closer to the target will get higher number, and away from the target gets some lower number using some formula. Now this is a reward, right? You have some path, and during the learning, say you are allowed to perform around 100 actions. Say you're allowed to perform 100 actions. You have done about 10 actions and you reach the target. So in the next cycles of learning, what should the model do? So generally in reinforcement learning, right, like before we continue, what you do is it learns by hit and trail method, and you give a reward for positive actions leading to the goal, and you also have a trade-off between the exploitation and exploration. In this case, right, like now you reach the target. In the next cycles of learning, the model, it can either follow the same path, which is exploitation. You have some learning and you exploit it for the next rounds also. That's exploitation. If you do that, the model ends up in getting more points. If you see the picture below, explore versus exploit, if you do exploit, in every round it takes the same set of 10 actions and gets +1, and finally in 100 rounds it gets 10 points. Exploitation will give 10 points. But if it does explore, in the next cycle it might go through a larger path and then gets a reward +1. But in some cycle it can get to a much shorter path. If you see here, it went through a path with 4 actions with a reward +1. So overall it has very less score, like 6 points, compared to the exploit throughout with 10 points. But this is more advantageous because you identified a shorter path, which is of 4. The last one you see here, 1 2 3 4, in 4 steps it can reach the target. So now if you're given a new exploit looks better, but for a new bot with 100 actions, say the learning is done, now you have a test set with 100 actions, it can earn up about 25 points using explore, because with 4 actions you reach the target and you get a +1. So in 100 actions you can do it 25 times and then you get 25 points. But if you followed only exploit, you have 10 actions to reach the goal, and then only 10 points you'll get. Right. So having a trade-off between exploration and exploitation is important in reinforcement learning, and model tries to learn from the rewards it gets. That's a brief introduction about the reinforcement learning. And then there's deep learning also, like supervised, unsupervised reinforcement, semi-supervised, and then deep learning is the latest improvements in the machine learning, and it's been there for a while now. It's used in all major systems currently. So you can see how Google translates translate the text into a different language in very less time. And customer support bots you see for the and speech translation, or in medical identification of cancer cells, or analyzing MRIs, or self-driving cars. All these are applications of deep learning. And there are some limitations, like you need a lot of data to train a deep learning model, and computational power also. You need GPUs with thousands of cores compared to CPU. So if you are a machine with just with CPU, it doesn't work. Like you need GPUs with thousands of cores, because it needs huge computation power. And we'll talk in the end about deep learning, especially about the neural network and the backtracking it does to learn the weights in the network. And time, it also takes a lot of time to train. Sometimes it takes hours, days, and months depending on the data. That's some limitations of the deep learning. Now let's get into each technique, right? Are you all with me? Raj, is it all going good?
Yes, sir. Everyone is interacting, so it's
Yeah,
going good.
sure. Okay. Supervised learning. First technique is linear regression. This is a basic algorithm you would learn if you are starting on machine learning. It's very simple. Linear regression just performs a task called regression. And regression is basically, it models a target prediction value based on independent variable. You have some independent variables and you have a new dependent variable derived out of it, and then you try to model this. That's linear regression. For example, this line equation, right? Y equal to theta2 x plus theta1. X is the independent variable and y is obtained from this equation. For example, in this graph, x-axis has the work experience, y-axis is the salary of the person. As the work experience increases, salary is increasing, and the regression line is the best fit line for the model. You have some data points. For example, say for work experience 5 years, you have some salary of 70,000. Similarly, you have similar other data points. Since it's supervised, you have the label also. You have the input features and you have the label value also, and the model tries to learn it and tries to fit a regression line that's best fit for the model, for the data you have. When they train the model, it fits the best line to predict the value of y for a given value of x. Once you have this line fit, you can see there are many data points, but we approximately fit a best line that represents all these data points. And now you're given a data point, say 10 years, then it goes onto the line and gets the corresponding salary, right? That's the prediction. So the model gets the best regression fit line by finding the best theta 1 and theta 2 values. Um, so you get the best regression fit line by identifying what parameters to use, and those parameters are learned during this training. Um, how the model is trained, right? Like you have a prediction, so the model learns by predicting and correcting it, and initially you have some parameter values, and model tries to learn and then corrects it, corrects it based on the error it has. So basically, say initially you have some theta value, and then the prediction goes, and you have a true value label also, and you have a predicted value also, and then uh, difference between these two is an error. Model tries to optimize this error, like reduce this error for best fit line. Uh, so cost function is the objective function you try to optimize uh, during the training process. And these are two terminology you come across, like cost function, loss function. Cost function is for the entire training set. Loss function is for a training sample. That's a simple difference. Here, cost function, we use mean squared error. You can see in the bottom here, minima is 1 by n predicted minus expected value whole square, and summation over all the training samples. You want to minimize this. This is the cost function, which we call as RMSE. It's very important thing in the machine learning stream. Root mean square error. Um, that's the cost function we have, and the equation for this is, you see it in the graph here. This is the equation, and you find the gradients at each step and try to subtract that from your theta uh, to move to the local minima, global minima. So the global minima is where the cost function is having the minimal value, and that's where you have the best fit line. So that's the theta you want. So theta on x-axis and cost on the y-axis. Say you are at this point on the top. Y hat is the prediction value, which is matrix multiplication of x and theta. So you can see y is theta x. Say you ignore theta 1, theta 2 x. Initially, say you have one parameter. Y hat is x theta, matrix multiplication, and then cost function is like we saw 1 by m into sum of this squares. And we put a half also, because when we take derivative, that 2 gets cancelled. So we say 1 by 2m instead of just m. And then to get the slope here, gradient here, you do dou cos by dou theta, and then this is the derivative you have, right? And theta is theta minus alpha into this derivative. So at each training step, what you do is you update the theta by alpha is learning rate multiplied by the gradient. So basically, if you're on the left side, the slope is positive, so theta is reduced. Slope is negative, and so negative and negative, it's positive, so theta is increased, and you move to the right. If you're on the right side, then the slope is positive, and then theta would be reduced to the back side. So in each training step, it tries to take you to the global minima here, right? And the learning rate is very important, because if the learning rate is too high, there is a threat of getting jumped from the global minima during the training process. Say it can reach to this step and then jump to the right side and never reach to the global minima. So if learning rate is too low, it might take too long for you to converge to the global minima. It might just stay here on the top of the graph and move by tiny bits. So it's important to have an optimal learning rate as well. So model tries to learn all these parameters well, right? So this is about the linear regression. So you optimize, and by the end of the training cycle, say you have the global minima, and then model takes that theta and gives you y equal to theta x, and then for a new x, it predicts the y value. That's linear regression. Now coming to logistic regression, right? Logistic regression use cases. So you use this to identify whether email is spam or not. will customer take loan or not, which brand watch customer buys. So logistic regression is used for classification problem generally. Uh, Generally for binary classification between spam or not, etc., yes or no types. And data is first fed into linear regression model, and then it's acted upon by some logistic function, here sigmoid function, predicting the target category dependent variable. So basically you want the predicted value to be between 0 and 1, a probability. So for that to happen, like if it's linear, it's not always between 0 to 1, right? So you take that linear and put it into a sigmoid function, and sigmoid is, you can see the sigmoid graph here, 1 by 1 plus e minus x. It's always between 0 and 1. So now the output of your model is always the predictive value is between 0 and 1, and I have some threshold like 0.5. It's greater than 0.5, the prediction, then you take it as S, and if it's less than 0.5, you take it as no, or spam or not, or whatever binary you're doing. And an activation function is used to convert linear to logistic regression equation, which we just spoke about, right? Say z equal to wxb, this is a linear part, and then h theta of x, where theta is a parameter and x is input. H theta x is sigmoid of z, sigmoid of the linear part, and this is the used for prediction. And the output of this would be a probability between 0 and 1. And types, there are like mainly three types of logistic regression: binary logistic regression, which we talked about, spam or not, etc. Multinomial logistic regression, it can have different categories like veg, non-veg, vegan, etc. Ordinal logistic regression, this is like multinomial logistic regression, but it is ordered, like movie rating 1 to 5, etc. Right? These are the three types of logistic regression we have. We'll talk about binary logistic regression now, because the other things can be deduced from this. Say you want to identify like 5 categories, you can always keep one category as pivot and break this into like two pairs and try to combine them with some formula. So coming to the binary logistic regression, right? Um, we don't use the same cost function as linear regression. So in linear regression, we used root mean square error, right? We don't use the same one, because for the function we have here, for the sigmoid function we have, if you apply root mean square error, you'll end up with non-convex function of parameter theta, and it will never converge to global minima. So converging is, you'll never get the optimal value. So you don't use the same cost function, root mean square error, but you have a different cost function here. For example, the cost function given expected y and predicted h theta x, the cost function is minus y log h theta x minus 1 minus y log 1 minus h theta x. So this is a formula you would come across a lot in machine learning, like especially for logistic regression. So if you see it later, like just remind of this session. Uh, uh, I'll explain you like how this makes sense here. Say y equal to 1. Say expected value is 1. Then the second part of the expression is cancelled of this equation on the right hand side. The 1 minus y, it would be 0. So you have only first part. So that would be minus log h theta x. So if y equal to 1, it's minus log h theta x. If y equal to 0, it's minus log 1 minus h theta x, which is the second part of the right hand side in the equation. So that's it. It's very simple. It's just minus log and minus log 1 minus h theta x and minus log h theta x based on y equal to 0 or y equal to 1. In general, like log x graph is this, and log y, minus log x is this, from top to bottom. And then if you apply the same for the cost function we have here, these are the graphs. For y equal to 1, it's minus log h theta x, which is like this. And for y equal to 0, it's minus log 1 minus h theta x, which is like this. These are the two graphs, and you can see why we came up with this, because if our expected value is 1, and as the predicted value goes tends to 1, our cost is 0, right? Because expected value is 1 and prediction is also close to 1, so we don't have any error there. So it tends to 0. And if the expected value is 1 and its cost is 0, it's tending to 0, then the error tends to infinity, because there's a lot of error, which is quite opposite to what we expect. That's why we use it here. And similarly for the second graph, you can see if the expected value is expected value is tending to 1, like expected value is 0, and then predicted value is tending to 1, then cost tends to infinity. But if expected value in the second graph, if the expected value is 0 and predicted value is tending to 0, then the cost is 0. That's why we use this cost function. Once you have the cost function, you can always take the gradient similar to linear regression, and then use that gradient to update your theta in every training cycle to minimize the loss. Right. So we don't talk more about those equations, but that's what you do. You take the gradient and update the theta values and learn from it, and ultimately you have the equation, right? This is the equation: h theta x equal to sigmoid of wx plus b. You learn the theta from the training samples, and then given a new x, using this equation, you'll find the predicted value. That's logistic regression. Is everyone with me? Let me know if you have any questions. Feel free to interrupt.
So do you want to? So there was a question, sir.
There's a question.
Yes, sir.
Okay.
With new libraries like scikit-learn, they have converted hundreds of lines of code to few lines, sir. So basically, we are using different modules, like for machine learning and stuff. We are using different modules like NumPy, Pandas, and we are creating models there. But most of the people, especially most of the developers, don't know the mathematics behind the machine learning models they are using, sir. So how much stress do you put on learning mathematics as a machine learning developer?
Right, right, right. This is a very, very, very good question. I would really encourage people to know everything behind the model, because if you're given a new use case, right, you would really know what model to use. And while you're using the model, when you go to the nuances of it, you know how the model works, and how to pre-process your training data when you're dealing on a huge scale, like millions of data, right? Especially at big companies. Um, you want to learn how the model works internally. Then it will help you to come up with new techniques to improve the model. If you don't know that part, right, like initially hit and trial, you get it, like you take some library and apply it and have the prediction, and you get a v0 model. That's fine. But when you improve it, you need to know the nuances of the algorithm. And also, like when you learn in depth, you can always come up with new ideas. You can always modify the algorithm, deploy it, and see how it works. And it's a huge deal to come up with a new algorithm, right? You can publish a paper, and people would reuse it. So I would definitely encourage to learn the math behind it, but try to get the idea, the gist of it. Like here we saw logistic regression, what's the cost function, and linear regression, what's the cost function, and how the gradient is computed. We have a gist of it, like try to have the gist of it, but also try to solve at least once, end to end, how the model is working. Once you understand it on paper, right, then using a library, it makes more sense. Yeah.
Yes.
Okay.
And also, sir,
Yep.
there was a question, sir, and it's about, will transformers replace CNNs in computer vision, sir?
Yeah, transformers are like latest in the neural networks, and they have been widely used. But the recursive neural networks and convolutional neural networks, they all have their own usage. I think it depends on the use case. Both are still used, but that's right. Like a lot of cases, I see transformers are modern, and then they have been used widely, and some places replaced also. But deep learning doesn't stop with these two things, right? Like there's a lot of new network algorithms coming up, and depend like many recommendation systems and search also has use cases with this. And main limitation is computational power. Like only mostly big companies tend to use this because they have huge computation power. Um, Small companies, if they don't have good GPUs and they don't go for complex techniques, they might still stick to simple networks or simple decision trees, right? Or other simpler algorithms. Uh,
Yes, sir.
okay. Any shall we get into the next slides?
Yes, sir. Of course, sir.
Yeah. Next is supervised learning, SVM. Which is support vector machine. I'm sure like many of you must have heard about it. It's a simple technique. The algorithm creates best line or like a decision boundary hyperplane that segregates n-dimensional space into classes so that we infer new data point into correct class. So say you have data points in the in the coordinate plane, and then you divide them based on a line, or if it's more dimensions, then you divide by a plane. That's SVM. Basically, SVM picks the extreme points of vector to create the hyperplane. Say here, right? These are the extreme points, the points closest to the other set. SVM tries to draw the line between these two so that the margin between these extreme points, the distance from the line to these points is maximized, right? SVM picks these extreme points to create the hyperplane, and then use cases are generally for face detection or image classification, text categorization, different places we use SVM. And there are linear and nonlinear. Linear is used for linearly separable data using single straight line. Nonlinear for non-linearly separable data. Uh, uh, Linearly separable data is like where you can draw some line and separate them. Non-linearly separable is like say the data is mixed, or like they are, it's a different dimensional. Says three, you have three features in the data set and it's a 2D plane. The hyperplane would be, and if it's two features, the hyperplane would be just a straight line. um, and you pick hyperplane with a maximum margin, maximum distance between data points. Like I said, the margin, the distance between the data points or points to the hyperplane, you maximize it, and that's your cost function objective. Also, you have the cost function, and it tries to maximize this hyperplane margin, uh, right? So in each training iteration, it tries to maximize this distance and ultimately come up with the final decision boundary. And the labels are like +1 for positive group and -1 for negative group. Um, Positive group is like if you have a new point, if you substitute the data point into the line expression, if it's greater than 0, then you give a label +1. If it's less than 0, you give a label -1. And everything between that, that is basically the margin. In the diagram, you can see this is the R2 like two-dimensional, and this three-dimensional. Here it's a line, and here the support vector machine, the hyperplane. This is a hyperplane, which is a decision boundary is a plane here, and the first graph it's just a straight line. The loss function that helps to maximum margin is called hinge loss. So for SVM, we use something called hinge loss. It's a famous and simple technique. Basically, if both the prediction and the expected value are of same sign, the point is on same side of the line or hyperplane, then the cost is 0 because it's correctly classified. You don't incur any cost. But if they are on of different side, different sign, you have to use some loss function. You basically have one minus product of the expected and the expect than the predicted values. That's hinge loss. And we also add a regularization parameter to balance the loss and margin maximization. For example, say, right, if the prediction is correctly done, then loss is zero. You wouldn't just leave the parameter theta unchanged in that iteration. Rather, we go and add a regularization parameter that would help to reduce the bias, or even the balance the margin maximization. So we have our main objective is to maximize the margin here, right? And derivatives of this are used to update the weights. Like the previous two algorithms, you take the derivatives of the cost function, and the logistic regression equations you can actually convert into SVM equations. And like in the logistic regression case, you have this graph, right? SVM also has looks similar to this, but a straight line. It goes till 1, and from 1 it's flat. Um, the cost function looks something like that, but you don't have to go into details of that, especially for this talk. So you got the basic idea of SVM here, um, uh, using the hinge loss and then taking the gradients and updating the theta, so that you come up with the best decision line. Next one is like unsupervised learning. One of the main examples of unsupervised learning is k-means clustering. All you do in k-means clustering is grouping the data points into k clusters. So you have to identify k centroids. Centroids are like real or imaginary locations needed. So you identify k centroids in your data points, and then your objective is to minimize the sum of distance between the data points and centroids. So once you identify k centroids, say you randomly pick k points in the plane, and then those are your k centroids. Now you start assigning the data points to these centroids based on the closest distance between the centroid and the point, and you take sum of all these distances, and that should be minimal. Based on that objective, you assign these points. So k-means clustering does mainly two tasks. One is finds best values for k centroids through iterative process. Initially, it's random k centroids, but later on, it keeps updating these k centroids using some technique, and then assigns each data point to its closest centroid forming cluster. So it assigns each data point to its closest centroid forming cluster, updates centroids using derivative of cost function with respect to centroids. Uh, so for first iteration, you pick the centroids, and then you assign the data point to the centroid. The closest centroid to a particular data point would be assigned. And then in the next iteration, you update these centroids using derivative of cost function. So you have the cost function, which is the sum of the distances. You can see xi minus mu I. Ui is the centroid, and xi is the data point. Distance between these two square, and it's a summation over all the data samples, and also it's over all these centroids, right? And then aij is 1 if xi belongs to j. If xi is assigned to a cluster j, xi is assigned to a cluster j, then aij is 1, and for the other cases aij is 0, right? Uh, uh, that's it. So basically, this is a summation of all distances between centroids and the data points. This cost function, when you take the derivative with respect to the centroids, that will give you give you some expression to update your parameters. Basically, the centroids. Let's see how the centroids are updated. Let's get a visual depiction, right? Um, Initially, say this is a point. Intuitively, you can say that this is one cluster and this is another cluster, but algorithmically, let's see how it happens. Initially, two centroids are picked randomly. Say this is one centroid blue, and orange is another centroid, random k centroids. Say k is 2 here, and then once you have the two centroids, in between these two, we draw a line, and that's your partition, and you assign data points to this. Like all the points here are to this centroid, and all the points here are to this centroid, right? Now you assign the data points. After you assign the data points, you try to readjust the centroids by observing the center of gravity of your section. So once you divide these sections, you on one side you have all blue and other side you have all orange. Now centroid actually moves to the center of this, so that you can see that it moves to center. It moves to center. That's the center of gravity of this section, which is basically you're trying to minimize the distance between these points. So if centroid moves here, right, once you try to reassign the points, uh, it goes to this center of gravity of this section, and then you have the new centroids as these 2 points, and now you reassign the points. You can see that a few points from the upper plane move to down, like these 2 points here come to become a part of the lower part, and that's how you minimize the distance between the centroids and data points. Now you try to readjust the centroids to their center of gravity, and then repeat the process. Draw a line again and try to divide in 2 sections and try to readjust the centroids. Ultimately, you can see this is the 2 clusters. The 2 clusters are correctly identified. Uh, so that's the k-means clustering. So you start with some random points, and then you iteratively you assign the other points. You start with random centroids and then random k centroids, and then assign the points, and then iteratively update the centroids using the technique, using gradients, and then reassign the values, reassign the data points to centroid. And it's unsupervised because you don't have a label. So the data points, you have only some features, and then based on the features you do some clustering. You don't have a label. Next technique in supervised learning is a random forest. Random forest is very important. You would see the application of this in many areas. Its training time is like comparatively less to few other algorithms, because you have different decision trees. So the idea behind that random forest is like you have different decision trees, and all these decision trees combine the output. They make some prediction, and you take the majority voting, and then that's your final output, right? That's random forest. Basically, it breaks the data set into separate chunks of data sets, and then for each data set, you build a decision tree. The model learns a decision tree, and then takes an ensemble of all these decision trees for the final prediction. So ensembling decision trees reduces overfitting by averaging the result. So ensembling the decision trees, it reduces overfitting. Basically, overfitting is when your training samples, when the model is too much fit to the training samples. Basically, it exactly represents all the training data, and then when you have the new data, it can flunk. So ensembling decision trees, basically you take average of all these different decision trees. So that way it tries to help you from reducing the overfitting. It's not exact always, like averaging would reduce some of that uh, overfitting issue. And each decision tree represents course of actions or decision through branches, right? For example, you have some features and some fruits, and then you have a feature called shape, and your decision is basically each shape round, and based on that you have the branches, if it is round or if it's not round. So apple and some other fruits which are round goes to one section of the branch, and other branch, the other fruits like banana and other things go. And that happens at every step, right? Like you have a node and you make a decision, and then you go to you form branches based on the decision, if it's yes or no. And how do you split data sets? Basically, you form a decision tree in a way that you reduce the entropy of the data set, right? Entropy is computed by the simple formula, negative of positive, total positive probability, like total number of positive samples by total samples, and log of that, minus total number of negative samples by total samples by and log of that. For example, you have only positive samples, right? Then log of, say you have 14 samples, 14 by 14 is 1, log 1 is 0. Your entropy is 0 if you have only positive or only negative samples. So entropy is high. Entropy is basically the unpredictability or randomness or impurity in the data set. So based for an attribute, if you're computing, right? If you have positive and negative half, then the entropy is higher there. If it's all positives, right? You know it's all positives. You learn from it, and then there is no randomness there. It's easy to predict there. So you take your attribute when you divide the decision tree, divide the branches in the decision tree in a way that you reduce the entropy or increase the information gain. We'll see in the next slide how you compute the information gain. So for a random forest, right, for a decision tree, so random forest is basically for a group of decision trees. Let's see how a decision tree is built. You begin with the tree, begin the tree with the root node, which contains a complete data set. Initially, you have a complete data set. Now you find an attribute using attribute selection measure. Based on that, you split the data to branches. And let's see what attribute selection measures are there below. Mm, uh, we'll go to that next. In the step 3, what you do is you divide the whole set into subsets that contain positive values for the best attributes. Generate the decision tree node which contains the best attribute. Right? So you break the S into subsets that contain possible values for the best attributes. Say your best attribute in this table is say wind. So wind could be weak or strong in this data set. So you divide it into subsets of weak and strong, and then have this in the decision tree. So the node says if wind is weak. If it's yes, the training samples go there. If it is no, the rest of it goes there, wherever wind is strong. And recursively make new decision trees using the subsets of the data set. So you have the subset of data set which are where the wind is strong and wind is weak. And now from this, you use another attribute to further divide it into branches, and you continue it until you cannot further classify the nodes, and the final node is called as leaf node. And let's say the attribution selection measure, right? There are two ways, like there are two measures, information gain and Gini index. Let's talk about information gain here. Gini index, you can have a look later. So information gain is very much used and popular. So information gain of attribute A over collection of S examples is computed by gain of SA, which is entropy of S minus. Information gain for a complete sample set A on an attribute A. For example, for this data set, right, you have different training data rows, and the attribute name is say wind. So information gain here is entropy of the whole set, which is this formula, minus. So initial entropy of the whole set minus. Say you are partitioning the sample set with an attribute A. Say here it's wind. Then you have to get that entropy, basically summation of different possible values of that attribute. For wind, it's weak or strong. Over that, you summate, you have the average of the entropies of that attribute. Basically, total SV is total samples with attribute wind as weak divided by total samples multiplied by the entropy of that sample set. Entropy is basically positives and negatives in it. So for this particular wind attribute, it can be weak or strong. For when it's weak, you can compute the entropy based on how many positive and negative it has. So when it's weak, it has a few no's and it also has few s. You can see, right, value of wind can be weak or strong. total entropy, for computing total entropy, you have 9 positives and 9 yes and 5 no. That's it. And then you can compute the total entropy with this. For S weak, you have 6 in the sample set. For the weak wind, you have 6 positives and 2 negatives. You can see that for weak, you have only two nodes here, and rest are 6s. And strong also, you have 3 positive and 3 negative. Now to compute the information gain, total entropy minus summation over the positive possible values for wind attribute, which are weak and strong, and their entropies. You can see entropy of S minus 8 by 14. 8 by 14 because you have total, for weak, you have 6 positive and 2 negative, so total 8 divided by total 14 samples multiplied by entropy of S weak. And also for S strong, right, you have total 6, 6 divided by 14 multiplied by entropy of S strong. And entropy, we have the formula. You have the total gain as this, and you do the same for all other attributes also, and take the maximum gain one, and then use that. Based on that, you split the branches. That's how you form a decision tree. And it's very important, like, these are the basic algorithms. Decision trees used many places, because of its high accuracy. We always like averages, right? Like, even one of the trees go wrong, when you take the average from different trees, majority voting can increase the accuracy of the model. That's about the decision tree. Any questions so far?
Yes, sir, there are a few questions, sir.
Yep.
Sir, there was a question, sir. Like as you said, using deep learning requires high GPU, like you said, sir. So what about us, the students who wants to learn deep learning? Like there are Google Colab for students, and what are some resources other than Google Colab that we can use to deeply understand deep learning, sir?
I see. I see. There is this notebooks, Jupyter notebooks. You can try to use to interactively learn these algorithms. It shows in live, when you run something. It shows the output immediately. And also, like, you have this PyTorch and TensorFlow, different things. I don't know if they have GPUs also, some test bed kind of thing where you have you can test your algorithm. But you can try these things. I need to explore, like, how much of it is open source. Like, if you have any platform to try your own thing. And also Kaggle is one place where people do machine learning contests. I'm sure, like, they must have some platform as well. Try Kaggle. Yeah. Many people do machine learning contests there. But I'm sure, like, there's a lot of scope here to improve the platforms and in the open source, for people to practice and run their own algorithms, uh, uh, because it's expensive as well, to get high powered machines with a lot of cores, and GPUs with many cores. Um, for students, I think Kaggle and Jupyter Notebook, or like PyTorch, TensorFlow applications, these would be initial sources to learn. A rough simulation is also fine, right? Like, you don't have to actually run on a big machine with higher data. Initially, you can always learn the algorithms with lesser data, or a simulation of it.
Yes, sir. And also, sir, if we are creating a project and we want to deploy ML, like we want to create a ML web app, what would be a better option, sir? Flask or Streamlit?
Flask, or what's the other one?
Streamlit, sir.
I see. I see. So this part, I'm sorry, like, I am not fully aware of which one is better here. You try to, like, look at the requirements there for companies, right? Like, Facebook has something called FB Learner, and every company has their own cloud. Like, Amazon has its own cloud. So we have our own clouds and we deploy there. Now, so I never got to actually deploy my own model outside the work environment. Basically, try to see which one is more adaptable and more resourceful when you because you have to train the model first, and how much like more the computation power you have, lesser the time. And then once you have the model trained, you have to deploy it and use it for inference. uh, Even for inference, you want to make sure the platform is supporting it well. Otherwise it can take too much time to infer, and it can break if your input is too high, right? Like if your model has many features, say if your model has 20 or 30, 40 features, inference can take longer on some platforms. Just pick the best based on these criteria.
Yes, sir. And we also have another question, sir. The question is that do ML developers need to have knowledge of another domain necessarily, sir? Like we can't just learn ML alone. So what is your take on that? What other domains ML developers should know, sir?
Uh, so, so the domain as in like definitely you can see that there's a lot of calculus involved, like calculus, coordinate geometry, all these things are involved. That basic mathematics to understand the ML algorithms. But in addition to that, you need to understand this system also, right? Like how you deploy it, and basically even the training the models, you have millions of data samples. You can't just you need some distributed systems to train the model on, or even inference time, right? Say you have your for search, when you're searching something, you have millions of profiles, and you need to pick the best top 10. Out of million things, you have to pick top 10 items. It's not possible on single machine. You need to do it on distributed machine by breaking your request to multiple servers. So here you need to understand distributed systems, how it works. So that's a back end thing, right? Also like visualization and all the implementation is generally in Python, or R, or different language, right? You need some expertise in the language, like at least understanding the Python basics is important. And also like you see some based on where you are applying this is also important. Some people apply in the biomedical industry, and some apply for self-driving cars. Especially when you're analyzing some MRIs or something, right? There some computer vision knowledge is important. I'm not a computer vision expert, but there are teams who work on this kind of problem, like tagging the images or something like that, classifying the image. There you need some computer vision knowledge. Um, so uh, like uh, so mostly the other domain requirement comes from where you actually apply your ML technique. But in general, like I know data science is emerging as as a field on its own. Like people are trying to go into data science, even if they are not from data computer science background. I know some people who are from aerospace engineering, and actually got into data science and doing pretty good. Yeah.
And also the participant adds up a question, sir. Uh, do you recommend learning cloud computing as a added domain for machine learning, sir?
Cloud computing.
Yes, sir.
I see. Uh, uh, yeah, that sounds like a useful thing, but I don't know what topics are exactly covered under cloud computing these days. But anything related to cloud is really important, because everything happens on cloud now. Your models are cloud, or on cloud. Like the training happens there. Like the saved model, you put it in cloud to do the inference, some remote prediction for the newer samples you have. cloud computing is important, like especially understanding the Hive and Presto, this Hadoop stuff, right? Like how you do the map reducing to process your data, which is very important. Like you have some raw data with millions of samples, and how would you apply map reduce to generate features out of it, to prune the training data features, and or like generate your final data set, right? Labeling out of it, deriving your label, or how you remove the noise in your training data. So a lot of things happens on cloud, uh, and you need to uh, know these things. Yes.
Yes, sir. And again, like you said, we should all the machine learning developers must learn mathematics as a part. At least they should know what's actually happening in the models. So a participant asks, how long do we need to put in learning mathematics or machine learning?
I see. I see. I would suggest like go from the use case. Like if you start reading everything, right, books and books, you will forget everything also. So start from something practical. Like what's the use case you are working on? Say a simple use case like classifying a email as junk or a non-spam, right? Or another simple case where you are developing a maybe a recommendation system. Say you have a user and you want to recommend him some movies or something. Say I like science fiction. I'm shown some science fiction movies, but I'm also from this era. I want to see newer movies from my interaction data or something. You'll recommend me some things. So this is the use case you have. Now go back and see what algorithms are important, and from there you try to go in depth, understand how they function. So that would be more useful, I feel. Um, uh, and then for some cases, yeah, where you don't have to go in depth, you are not using it right away, it's okay to understand it superficially. It's like DFS and BFS, right? Like you go depth first search and you go deep and deep and deep, and you get stuck there. Then there are a lot of other important things on the surface you would ignore. Rather, I would say in my talk, you have some understanding of k-means clustering, and you have some understanding of SVM, support vector machine, logistic regression, linear regression. If we spend all the time in linear regression, going equations and gradients, it might consume a lot of time and energy. Uh, so I would say, like, it depends. If you have a big vacation you want to spend on, then do all mathematical equations. But if you are juggling through other things, try to understand superficially, but get into the practicality of it. Apply the model practically in some use case, and for that, try to contrast the different algorithms you have, and then try to see which one works the best and understand how they work.
So you're saying too, we should learn math behind the machine learning model depending upon the projects that we are making.
Yes.
Yes, sir.
Yes. Yes.
There's one more question, sir.
Yeah.
How important is EDA, sir? And how to balance precision and accuracy in training ML models?
How important is what? EDA?
Yes, sir.
I see. So precision, right? Like it's basically balancing precision and recall, not accuracy. Like precision is generally accuracy. Um, so being precise is basically being accurate on something. Uh, in say you have different layers in your machine learning system. In the initial layers, you want to have the recall higher, and in the final layer, when you are throwing something at the user, you want to be more precise. So both are important. For example, right, uh, you are generating some recommendations, say on Amazon, or for a user, you are giving him some products, right? So there are three layers. Initial layer, or let's look at some friend recommendations, right? So there is some social network website, and it has to recommend friends, and from different data sources, it has, say, data source 1, 2, 3. It has some profiles from there. Uh, it has a million profiles from each of them. Now your initial model has to have more recall, so it has to be little lenient and increase the recall. So it doesn't have to exactly match what you want and what you need. If it is search, it doesn't have to exactly match to the query. It, not about the query, but other signals like social signals and other signals. It can be little lenient and increase your recall. So basically, something correct should be in your output, rather than being so precise and leaving something good behind. Precision is where, if you have 100 items and you 10 of them is what you need. If you have and the output has only 5 items, if all 5 items are precise, right, are all correct, that's precision. Like, um, out of everything you get, you want to maximize the correctness. That's precision. Recall is you want to maximize amount of correct items you have in the output. For example, if you have 10 items, you take 25 items in the output and make sure more correct items are in it. Say if you take 20 out of this, maybe you have 8 correct items in it, right? This is a higher recall. You have other junk also here. uh, you're getting it, right?
Yes,
So
sir.
yeah, say you mix two grains, right? Say you mix some pulses and rice together. Now you want to separate pulses out of it. If you're hand picking pulse by pulse, you might get 10 pulses into your hand, and this is being precise. But if you just take a handful of stuff, go to an area where there's more pulses and take it, now you have more pulses in it, right? But it's mixed with some grains also. This is recall. So you what you need, the pulses, you have a lot of it in it, but it's mixed with other things also. Now in the next step, you apply precision, right? Initially it's recall. Now you apply precision, and then uh, just filter out the unnecessary things from there. So both are important, but you go in this order. Like if you have different layers, you apply some algorithm to get more recall, and then another algorithm to get more precise items.
Yes, sir. That was a great answer, sir.
Okay.
And also, sir,
Hmm.
sometimes there is errors faced in training models with large data sets, sir. How to deal with those kind of errors? And is reducing the number of columns is the way to go? And to what extent we can reduce the columns or features in order to prevent the errors?
When you say errors in the data sets, right? What could be that? I think maybe it's removing some bias and things like that. Uh, uh, there could be some errors, yes, like some labels could be wrong. So I think one of the techniques is like decision trees. The having an ensemble is really helpful to handle cases like this. Say if you divide the data set into different sets and you have different decision trees predicting, now you take the majority of the answers, right? So even if one of them is error completely full of error, other things would predict better, and you take the majority decision. So there are algorithms especially towards this, and then taking an ensemble is a way to go for preventing errors. And also like XGBoost, and there are different techniques. You do sequential trees also, and you correct the errors in the previous one. Those are some way to go. Yeah.
Yes,
And
sir.
reducing the columns, is it a good idea? That depends, right? Like there are different parameters. The hyperparameter tuning is very important. Even we do. Um, uh, when you have a higher computation power, you can actually clean sweep. We call it as sweeping the parameter sweep. Basically, you give some ranges for each parameter, each column, and each parameter, and then it tries different values, and picks the best one, which has the highest metric we desire. Like our metric is NDC or whatever metric, we have the model evaluated upon the test set. Whichever parameter combination gives you the best, you take that. So if it's working best with lesser columns, you go with it. But lesser column doesn't necessarily mean it's the best model always. So it completely depends on the case by case. Yeah.
Yes, sir. Thank you, sir.
Okay. So next, let's get into the next slide, which is we'll wrap this up in time. We are almost there. So bias versus variance. Like you hear a lot about bias and variance. Bias is like inability for an ML model to capture the true relationship. For example, in the first graph you see here, there are different data points, and you fit a line, say through linear regression, you fit a line. The inability for a machine learning method to capture the true relationship is called bias. You can see that it's not capturing exactly. There are some data points up and there are some data points down to the line. It's a average of all the points. So there is some bias here. That's bias. Bias is basically where your model is not completely fit to the data points. It's roughly representing it. And what's variance? Variance is difference in fits between the data sets for a model. So say you have some data points and you break them into training set and test set. Say the blue points are train set and green points are test set. So say when you fit the model to the train set, you have a curve, exact clean curve like this, right? This is good, this is perfect. But when you switch to the test set, you can see there's a lot of variance. The representation is not exact, right? This is variance. When you change the data set, there's a lot of variance. But in the previous case, right, like even if for the test set, the distance between the line and the points summation wouldn't be too high. It's comparable to the train set. Here variance is less, but here where the curve exactly fits, you can see there's a lot of variance. That's bias and variance. Variance is like with the data sets, if the model fit to the data set changes, that's variance. Bias is like inability for an ML method to capture correctly the relationship. It's a famous way to explain this using a bullseye. Some of you might have seen it in some books. Um, you know, this archer tries to hit the bullseye, right? Say in center you have the target and the blue points are the predictions. In the first figure, right? First figure, all the points are close to the true value, target value, which means the model correctly represents, right? Represents model correctly represents to the true data set, true labels. So the bias is low here. Also, you can see the data points are so close, and all the data points act similarly for the model fit. So the half here and half here both are almost in the similar section. So variance is also low. In the second first row second diagram, right, you can see that all the points are very close to the target still, so bias is less, but variance is high. If you consider the points closer to the target here and consider the points away from that in the on the second circle, they both are different. Like they both seem to represent a different model, right? That's high variance. And second row first figure, right, you can see that all the points are together, the variance is less. All of them almost represent the similar thing, but they're all away from the target true label. So the bias is high. They're not truly representing the data set, but all of them represent the same similar thing. And then second row second figure, you can see that the variance is high because the points are spread across, and also there's high bias because they're all away from the true target. Yeah, that's about bias and variance. And overfitting and underfitting. Overfitting is model fits too well with the data but fails to generalize learning. Underfitting is model doesn't fit well with data, it's trained on even. For example, this first diagram, it's underfitted. This line and the points are spread across. It's not exactly representing the data set. And third diagram, it's overfitted. You can see the line curve goes exactly through the points. Now, if you're given new test set or something, it can flunk. The middle one is a good fit. You can see an approximation of the curve through the data points. So say it's you are given new points around that, it might work similarly. So we close it with the artificial neural networks. So the neural networks are used in majority of the cases today, use cases. It's modeled after human brain, the way we have neurons and stuff. Neural network has a connected neuron setup, and it trains with some process. It's used in image recognition, speech recognition, medical diagnosis, and many use cases currently. And there are three important layers. One is input layer, which can take text, numbers, audio files, image pixels, etc. And then in between there's a hidden layer. It performs computations and recognizes patterns in the data. Um, Perceptron is a special neural network which has only single hidden layer. It can have multiple hidden layers as well. And output layer, it obtains the result of computations, right? So there's a transfer function that computes a weighted sum of inputs and biases, output of which goes through activation function like sigmoid, ReLU, softmax, etc. So in the neural network, the computation is done through some equation, like at each node in the hidden layer, at each neuron, you have the transfer function applied. Basically, take the input and some weight, and then multiply them and sum it over all the neurons, branch it towards the next layer. And then you take this output and put it through some activation function like sigmoid function, which gives you a probability between 0 and 1. Um, and then you have the final output, and you have an error function, like say root mean square error, right? You have a true label for supervised learning, and then you have the prediction value, and it tries to generate the error and tries to minimize it. Initially, you start with some random weights, and then you correct these weights based on this using a technique called backpropagation. So based on the error function comparing predicted and expected output, we adjust the weights through backpropagation method. So once you have prediction, after the feed-forward network computes and gets you the final value, a final prediction value, you try to compare that with the true value, and then you take that error and try to correct that backwards. You apply that gradient backwards so that all the weights are corrected across the path. There are two types of networks: feed forward, like data movements only in forward direction, and there are some other networks like recurrent neural networks which has feedback loops. Data is sequential or time dependent in these cases. So there are feed forward and feedback networks. uh, let's talk about main technique here, main algorithm, backpropagation for neural networks. How it works is, say, take this simple neural network. You have input x1, x2, you have a hidden layer with h1, h2 nodes, and then output layer is y1, y2. And you can see there are channels from x1 to h1, x1 to h2. Similarly, x2 to h1, the channel has weight w2, and x2 to h2 channel has weight w4. And h1 to the final output y1, you have a channel of weight w5 and w7. And h2 to y1, it's w6 and w8 to y2. And there's a bias at each of these, b1 at the hidden layer and b2 at this layer. Mm. And output at h1 is basically weighted sum of these inputs plus bias. And then output h1, final output is basically, it takes this transfer function output into puts it into an activation function like 1 by 1 plus e power minus x sigmoid function. So you can see the output at h1 is 1 by 1 plus e power minus h1. Same way we get a y1 and y2 also with h1 outputs as inputs, h1, h2 as inputs. So that's your final output. Once you have the final output, you compute the total error. Error total is summation of half target minus output square, similar to root mean square error we saw in the previous algorithm. You have the target. Target is the true label for a given data set with the features x1 and x2 values. You have some true labels at y1 and y2. You subtract that with the output you have currently through this formulas here, through the activation function formula, and you put it in the equation. That's the error. Now you do a back propagation. Basically, you identify some error at each weight, because weights are the variable things, right? Inputs are constant, so you want to modify the weights. So for each weight, you find a gradient, which is dou e total error with respect to differentiation of this error with respect to weight 5. So you take the differential of the error with respect to weight 5, like what's the contribution of this error because of 5, you get that gradient. And to compute that, you have the apply the chain rule. You take the differentiation of E total with respect to out y1 because it has out y1 as the parameter, and then you multiply that with out y1 as a function of differentiation of out y1 with respect to y1, and then y1 with respect to w5. And you know y1 with respect to w5 because it's the transfer function is based on that. Um, so y1 is a combination of w5 and w6 as well. 6 gets cancelled and only w5 term remains, and you get the differential value. So once you get the gradient, the differentiation of total error with respect to that weight, you subtract that from the initial W5 by multiplying with an a learning rate. We saw a learning rate, right? It helps to converge faster or slower. So having a optimal learning rate helps you to converge at an optimal rate. And similarly, you do this with all weights here. That's why neural networks, they need a lot of computation power, because this back propagation, this is done at every channel on every weight, and it corrects the weight with every training sample, say. And it needs a lot of data to learn this also. You have millions of samples, and it does this back propagation on every sample, and it does need a lot of computation power, and it takes a lot of training time. That's about artificial neural networks. And I'll end this by giving you my contacts. You can add me on LinkedIn or Facebook. I'll just put this uh, into the stream. Is there a way I can put this in comments to everyone? Or Raj? I'll put it in the host room, right? Private chat. Yeah, you can pass it on to users,
Yes, sir.
students. Okay. Yeah. So these are my contacts. You can feel free to add me if you have any more questions in general about career or job search or machine learning in general. You can feel free to. Any other questions we have?
Yes, sir. I would like to pick a question from the participants. There has been a buzz around creating neural networks and reading and writing data on the human brain, sir. So, and there's also Elon Musk's Neuralink. And what do you think about it? Will it create the new next human evolution?
Hmm. So basically, neural network writing on human brain. Uh,
Yeah.
I see. So this part I'm not really sure, because I believe that humans, uh, we are a separate power, and our life is different. Like, we can emulate our brain and do a lot of things, but actually creating superhuman is not so easy thing to do. And I can presume a lot of side effects of it as well. But
Yes,
if
sir.
people are experimenting on it, I'm no one to talk about it. Definitely, but I would prefer not to alter myself. uh, uh, we are special in our own way. But it's true that there can be a lot done with machine learning. Um, and the neural networks, and like, just take self-driving, right? In India, self-driving, it's still a long way to go, and so much can be done with the Indian traffic and the roads. How can we actually apply neural networks and machine learning, artificial intelligence, to make this self-driving possible? That's one thing. And drones for the deliveries and all that stuff. Um, and also the way we are using gadgets today, right? We are having a computer with us, a mobile with us, carrying all this hardware everywhere, right? Can we simplify with that? Like, there's so much happening on AR, VR also, virtual reality, augmented reality. um, Still there, and then health applications, right? Even today, still there are physical doctors, and how can we apply more AI to automate a lot of this stuff? So there are a lot of other good applications to make a human life a better world, a better place for humans, right? To improve the lifestyle of humans, we can still we have a lot of scope still.
Yes, sir. That was a good answer, sir. And we can move on to our giveaway session, sir.
Yeah. So giveaway session, right? Like we spoke about a lot of algorithms here. I would ask a simple question out of my session. I wouldn't ask you anything fancy that you have to Google, but don't Google. You would find. Don't Google it. So the question is, so if you know the answer, just type it in the comments, and Raj will pick up whoever wrote it first. What is a loss function that's used for SVM, support vector machines, called? What is the name of the loss function? Did you get an answer from anyone, Raj?
Up to now, not until now, sir.
What's the loss function used for SVM, supervised machine learning algorithm, SVM, called? Just don't Google it. Like think about our session, and SVM is where we have the decision boundary, a plane and a line, right? And we spoke about a loss function. If it's of same sign, uh, the prediction is correct and loss is zero. Otherwise, you have some loss to be incurred, and you call this
Uh,
loss function as something.
we got an answer, sir. Roshan Teja said hinge loss.
That's a correct answer.
Yes,
So
sir. So Roshan
Roshan,
Teja,
yeah, Roshan Teja is the winner then.
yes, sir. We can wrap up our session, sir.
Cool. Thank
Thank you
you,
so much for
everyone.
coming here, sir. Thank you so much for coming here, sir. It's been a pleasure for us. It's been a really enlightening session for machine learning enthusiasts like me and also the fellow participants. And we wish to see you again in one of the events like this, sir. Thank you so much.
Cool. Thanks, Raj, for helping with the session. See you. Bye.
Thank you, sir. Thank you for participating in this session, everyone. Thank you for interacting. And I kindly request all of you to go and fill out the attendance form. Only if you fill out the attendance form, you'll be permitted with the OD, and you have to attend all the events to get the OD completely, and you have to fill out the attendance form. And now I want to talk about our hackathon Technica. So this is our hackathon, guys. It's a 48-hour hackathon. It's happening at the evening. You can actually participate it right now. I think the links will be given in the comment section or chat box. Like I said, it's a 48-hour hackathon where you will ideate, innovate, and inspire the future generations with your projects. And we wish to meet you there. Once again, I thank everyone for participating in this wonderful session. Have a good day. Have a great weekend. And have a great horizon. Thank you.